Fellow Physics 182 students, Professor Jeff Wilkerson once again here. For those of you who aren't Physics 182 students, I'll get tired of saying that sooner or later. What we're going to talk about today, this is a little bit more of our laboratory work we're going to talk about here right now. And what we're going to talk about is making histograms. And I know you've done this a little bit, but we're going to push this a little bit further. We're going to really work on this semester. And we're going to make histograms of measured quantities, measured variables that we've measured in the lab, and we're going to practice fitting Gaussian curves to those to try to understand the histograms, understand the data a little bit better. And we're going to talk in this video just a little bit about what the advantage of doing this is over doing the sort of straight up column statistics you've been doing, just finding the mean and the standard deviation but algebraically, by doing that statistically. There are advantages and disadvantages, and I honestly recommend you always do both. And some other things too, as we'll talk about more as the semester moves on. Process your data every which way you can and look at it and turn it upside down and twist it and pull on it and ask yourself questions about it. This is what you do. But right now, you all are engaged in measuring the index of refraction of glass for various colors of lasers and trying to make as good a measurements of those as you can and tell if you can tell the difference, determine if you can tell the difference between the indices for one color of light for your glass block and another color of light. And this technique of fitting Gaussians to histograms should serve you pretty well. So let's talk about the sort of what we're thinking about as we do this. And that is to say, you're going to end up, let's suppose you end up with 70 or 80 measurements of N for one of the colors of light. Okay, so you've got these 70 or 80 measurements of your index of refraction. That's what N is there. Measurements of your index of refraction. And you want to try to determine what your best estimate for the index of refraction is. You know from 181, from the first semester of the course, one good way to do that is to take the mean of that distribution and to say the uncertainty in the mean plus or minus is the standard error of that distribution, the standard deviation divided by the square root of the number of trials that you have in here. One way to approach finding that mean and standard deviation is to make a histogram of these values. And I think you made histograms in Physics 181 too, as well, but we'll talk about them just a little bit more. All you're doing in making a histogram is creating a series of bins, and we want those bins to all be the same size for the purpose of what we're doing here right now. And to say you're creating bins, and a bin is just a box you're going to put these N values in. And so if your box is, I'm just choosing a random example here. It's not random. That's another thing we need to talk about. It can't possibly be random because I'm thinking about it and choosing it, but it has no particular bearing on what we're trying to do here. And so let's suppose that all of your values, I don't think they will, but let's suppose all of your values fall between 1.40 and 1.52, okay? So you have all of those values. You might start by making bins that go from 1.40 to 1.41, and everything that falls between 1.40 and 1.41 goes in there. And then your next bin up is 1.41 to 1.42, and everything that falls between 1.41 and 1.42 goes in there, and so on and so on and so on. And in that way you'll have 12 bins. That seems like probably a pretty good choice with this number of data points, and it's a good place to start. But I'm going to recommend it. In fact, I'm going to give you homework that asks you, it's a little bit stronger than just a recommendation. I'm going to give you homework that asks you to make the histograms with different bin sizes and try to fit Gaussians to each of them and start to learn what's going on in those situations. So you make these bins across here, and you stick the data in there, and you end up with something that looks like this. A graph that is the number up this direction, and on this axis, you've got your various bins, and so you've got this 1.40 to 1.41, and suppose there were 5 in there, and you come up here, and you draw a line across at 5, and then the next one, 1.41 to 1.42, if there were 6, you go up one more, and then if there were 14, between 1.42 and 1.43, you go all the way up to 14, and so on. And you get your histogram that looks like this. Now, when you have your histogram here, what we're going to do is we're going to try to fit a Gaussian to this histogram. And I'm going to ask you to do it both in MATLAB and in Kaleidograph to fit the Gaussian with your homework. Both Kaleidograph and MATLAB, you have to do a little bit of twiddling. You have to do a little bit of setting things up in order to make this work. But they're both set up for you to relatively easily fit a Gaussian to this distribution. So you've got your histogram, and you fit a Gaussian here. You have to give it starting values. You have to give it guess values. Okay? So that's your Gaussian curve. It's a functional form. If you look at Hughes and Hayes, your textbook for the lab component of this course, if you look on page 24, so on page 24, they give you the functional formula for that that says if it's probability, it could be scaled to total number like we have here. It could be scaled to probability to fraction. So if you integrate it up, you get 1. If you have a probability distribution, that probability distribution looks like 1 over sigma times the square root of 2 pi e to the x minus mu divided by 2 sigma squared, where sigma is the standard deviation and mu is the mean of the distribution. And that whole thing's squared as well. And so that looks like your distribution. I've changed their variables a little bit to look more like what we tend to use. But in any event, that's the distribution. That's the functional form of that fit that's going on there. When MATLAB or Kaleidograph or Python or anything else that you're using is doing this fitting, you should do this in Python too if you've got Python familiarity. I do it in my lab. We work with a programming language called IDL, and we do this all the time in IDL. So we do this all kinds of different ways. What you're doing, imagine doing this functional fit. So you're giving the program, you're giving the code, whatever code it is, starting guesses for this mean value and standard deviation value and whatever this scale factor is out front. And as you're doing this in class, I can walk around and help you get some of these starting values. So for example, those are some of the things that you need to give it. This scale factor out front, I often have an offset factor. That's cheating a little bit, and we'll talk about how that's cheating. But give it an offset factor to let this float up or down, to say there might be a background noise in here. The background might not be 0. The background might be 1 or 2 across there. So I'll often have this plus some background that this thing sits on top of. So we have these various things, and we give it starting values. And the reason we give it starting values is think of these different values. The best mu. It's trying to find the best mu, the best sigma, the best background, the best factor out front to get the best fit. And by the best fit, what we're really doing, and we're really going to work on this semester. So you'll hear from me a lot more on this. This is just the very, very beginning introduction to this. But the best fit is measuring sort of the deviation at each point across there from the fit curve like that. How much above and below was that? And we're measuring that deviation of the fit from the actual data, and we're trying to minimize that deviation. Okay, and so when we minimize that deviation, you can imagine you've got all of these different variables that you're playing around with. You can tweak each of these little variables, and as you tweak each of these variables, you either got better or you got worse. Okay, and so if you think of this as like a rubber sheet with all of those variables, there are all kinds of local minima. And so so what it's doing is it's saying, it's getting better. I'm moving down this minima. I'm moving down until I find that local minimum. And when I find that local minimum, I'm going to quit. But that local minimum might not be the minimum you want, and it might not be the best minimum right there. So you want to start pretty close to the value, as close as you can to these values, so that it can measure the curvature of that sheet. What's going to happen more likely than not, if you don't start close enough to that, you're so far away from the actual values, that tweaking those values just a little bit doesn't change anything, and you're just wandering out in the desert. You're just drifting along, and you're not finding any curvature in that sheet. You're not finding any better fit. Follow the curvature till it's steeper till you hit that bottom. Okay, you're not finding that. You got to get close enough to that in order to find it. So we give that the starting values, and we find it, and that's what we're going to be working on here over the next couple of weeks. All semester, but that's the starting point over the next couple of weeks. Now, the reason we do this, there might be multiple reasons we do this. And again, I recommend you just do your straight up algebraic statistics here, and you do this kind of fitting as well, and you compare the results, and you think about the results, and you make decisions about which you want to emphasize. Don't necessarily choose one over the other, but emphasize one over the other when you're thinking about the analysis of your results. One of the reasons we do this is if there are extreme outliers, like that, or out here, you've got these points that are way off. Those can really change both the standard deviation and the mean of this distribution. They can really pull this distribution around. It's an effect that I call the tail wagging the dog. Okay, that tail can really wag that dog and can change your mean significantly. Now, if you're doing a fit, this fit has to try to incorporate this and this, and it can't do that, right? I mean, it can miss this one point by a lot, and still basically it's gone to 0 by that point, and so it's not missing by a lot. It's 1 versus 0, but it sort of goes about minimizing the impact of these outliers. And your mean is right here, and your standard deviation is across here. And with that mean and standard deviation across there, the impact of these outliers is minimized significantly by doing this fit. Whereas here, you can really jerk this thing around, okay? And so it's a way of trapping outlying data. Is that fair? I don't know if it's fair or not, right? You have to make these decisions again. We have to look at the data and make the decisions. But generally speaking, I tend to try to do this when I can. Now, the trick is there's a lot of ways that this can fail for you, or if not exactly fail, can be problematic for you. So this is all great. This only works if you were measuring the same thing every time. If you weren't measuring the same thing, as we get later in the semester and we're working in electronics and you're measuring the voltage, one of the things you're going to realize, the potential difference across some device, as that device heats up, as surfaces charge up, as things go on there, that potential difference across your resistor or your capacitor or your light bulb or whatever we're working on in that particular experiment can actually drift with time. And you're not measuring the same thing. It's actually changing on you. And so this can be changing, and you might not be measuring the same. But that's a problem over here, too, of course. Yet that's not unique to fitting the Gaussian to a histogram like this. So that's an issue you got to deal with. It may be this works great. We would expect, and your book talks about this, and we can talk about this some more. We would expect this to have a nice, normal Gaussian shape like this if what you have is some real value that you're measuring, and the distribution, the spread here, is due to stochastic noise. It's due to random noise. Is due to what we're calling statistical uncertainty. If it's just sort of a real measurement noise in there that's causing this spread, Gaussian is probably the shape that this is going to be. But it may not be that. There may be something else going on, and the underlying function, there may be a real functional relationship of something right here, and the distribution of the things you're measuring may actually look like that. And if they look like that, then you can fit all the Gaussians you want to, and it ain't going to work, okay? And then you have to figure out what that real functional form is and fit the real functional form under there. But that's a topic for down the road. We are, in this second semester class, we're going to spend a lot of time focusing on this, with the understanding that there are complications that we may have to pay attention to, but we're not going to deal with those complications significantly right now. We're gonna maybe late in the semester, as we start to transition into the third semester, we'll start to deal with this just a little bit, and then you can pick some of this other stuff up. It may be that you want to be able to fit two Gaussians, and we'll do some homework later on, where you're actually measuring two different things, the convolution of two different Gaussians, and so you would actually fit a Gaussian and a Gaussian that overlap like that. So there's your convolution of two Gaussians, and you can just write the software to take this plus another one of those, right, and do that fit, and that's all coming down the road for us. One of the biggest problems we run into in fitting the Gaussian is we simply don't have enough data. You need to have a reasonable amount of data in several bins, and I usually like to have around 7 bins right here that have a reasonable amount of data in them so that this Gaussian fits. If a bin doesn't have enough data in it, it's got noise, and it's got really what's the equivalent of Poisson County statistics noise in it. And again, we'll deal with this later on. But to say, the uncertainty, if a bin has 3 counts in it, just think about this for a moment. If a bin has 3 counts in it, the uncertainty in that 3 counts is pretty significant, 4 or 5 or 1 or 2, or you can see that. Whereas if the bin has 400 counts in it, the uncertainty is relatively small. It's going to be related to the square root of the number of counts. Again, this is a topic for us down the road, but you can miss by 20 or 30 or 40 if it's got 400 in there, and it's not a huge difference like that. Okay, it's not a huge distinction in terms of where it falls in this distribution. And so noise in these bins messes these things up and causes these fits to be problematic. So the art in making a good histogram to fit a Gaussian like that art comes in choosing the right number of bins so that you have enough data in each bin so that you're just not eaten up by random noise bin to bin. You don't get something, if you've got 3 or 4 counts per bin, oftentimes it looks like this. And sure, the underlying result might really be Gaussian in nature, but you can't tell it because you just can't. You could fit almost anything to that. You could fit a flat line across there pretty well, and say that's great. You've got to be able to see the shape of this curve. You've got to have enough data in here, okay? And you've got for the fit to be robust with 1, 2, 3, 4, depending on what else you might do, but 3 or 4. Variables that you're tweaking, you got to have enough degrees of freedom to tweak those things. You got to have enough bins right here to be able to tell what's going on, to really be able to measure. If you want to really be able to measure that sigma, that width across there, right? You got to have enough bins to be able to measure that across there. Have significant amount of data. Again, I think 6 or 7. 7's probably a minimum number for what you want to be doing right there to have a reasonable amount of data in there. But if you take 70 points, you already see the problem. If you take 70 points and you split it out into 7 bins, that's an average of 10. And if this middle one's got 30, then you've got some out there on the edges that have just a few. And so the work you have to do, the real science you have to do right there. Again, people call this artistry, but you watch one of the earlier videos, the lab theory video, and you understand that it's not art, it's science. It's the part of the hard part of science, the decision making of science, is to try to get the right number of bins in order to make this thing work the best that you can. And to do that, you often just need a lot of data. You need an overwhelming amount of data. You can see why 70, it seems like plenty, but when you start doing this and start breaking this out into bins, 70 just simply might not be enough. 100, 150 is a lot better. So if you could find a way to get 150 measurements of this thing, and again, you're working in lab, so that means each of you taking 3, each of the 3 of you taking 50 measurements, you might be able to get 150. But then you have to worry about if you're not all doing it exactly the same way and doing the same thing, then this end value isn't the same. And you might actually have 3 different histograms right there. And so you have all kinds of complications. You just got to navigate it, and you got to do your best work and make your best decisions. But you want to get as much data as you can so that these bins, you can get as many bins as you can up here that have as much data in them and aren't as noisy as you possibly can to make this fit as robust as it can possibly be. And we'll be walking a line all semester long about whether we have enough data or not, whether it's better just to do your algebraic statistics here or better to do your Gaussian statistics here. And again, I urge you to do both. Compare one thing to the other. If nothing else, doing the algebraic statistics gives you the starting values to estimate the fit over here to make sure you get a good, robust fit. So that's what we're going to try to do, and we're going to start that with this first experiment. We're going to do it with every experiment that we do here this term. And so we want to practice this idea of starting to try to get a handle on how we can do a better job of measuring the mean and the uncertainty of these variables, of these quantities that we're measuring. So that's what we got for you today. Histograms and Gaussian fits to those histograms. We will be talking more and more and more about this all semester long.